All right, so we're going to start off looking at section 3.5. So we're in the middle of chapter 3 on finding roots of polynomials. Last time we learned how to use synthetic division, rational root theorem to help us, to help us find roots. We're going to do the same thing in this section, except now the roots could come out to be imaginary. Okay, so just a reminder of what a root is. Okay. It's something that you can plug into an equation, and when you plug it in, it comes out to 0. Once you know what that root is, it also tells you where it crosses the x-axis. Okay, so if you write the number of your 0, or the number of your root, put a comma, and then put a 0 after it, that's going to be your x-intercept. Okay. If you draw a polynomial and it does not cross the x-axis, it doesn't mean that there aren't any zeros. What it means is that there's no real zeros. Okay, so think of a parabola like that. There are no real numbers you could plug in that would make that 0. And I know that because I'm looking at it and there's no x-intercepts. So maybe that's the equation like y equals x squared plus 1. Okay, it's a parabola and it's been shifted up. Okay, maybe 1 unit, 2 units, it doesn't matter. Let's set that equal to 0 and see what happens if we try to solve it. We already know it doesn't cross the x-axis. Okay, so let's see. So Dex, what would be my first step to solve that?
To get the 1 on the other side.
Yep, and what would that give me?
-1 equals x squared.
Perfect. -1 equals x squared. And then my last step, what would be my last step?
The square root of both sides.
Yeah, so we take the square root of both sides, and then when I take the square root of both sides, Nick, what's going to happen?
Imaginary number. You can't get a square root of the negative.
Well, you can't take the square root of a negative and get a what kind of answer? If you take the square root of a negative, you'll never get a
A real number.
yeah, you won't get a real number, but you could get,
Imaginary.
yeah, you could get imaginary. So that's what we're gonna talk about a little bit. Okay, so this is an example where an imaginary number could come up when you're trying to solve an equation, and you end up taking the square root of a negative. So let's try to do that on the calculator and see what happens. Let me get the calculator. Alright. So I'm going to type in square root of -1. Square root of -1. And it tells me, it doesn't say that it can't do it. It just says that the answer is not real. So what I can do is if I press mode, and instead of telling the calculator to work in the real number system, I'm going to tell it to work also with complex numbers. Okay, that's the a plus bi that's next to it. So if that's under mode. It's the button right next to second at the top. Okay, so if I put it on a plus bi and I type in the same thing again, this time it's not going to say non-real answer. It's going to tell me that the square root of -1 is I. Yeah. All right. So now let's see what happens if we plug I into that equation and do it out. Right. And I'm going to explain more what I is, but for now I'm just going to do it on the calculator. So I'm going to take I and I'm going to fill it in for x, and let's see what happens. So I have second, the decimal point, that's I, squared, plus 1. I just got 0. So that means that I is a what? If I plug it in and I get 0 as the answer. Moises? That's not a factor because it's not, to be a factor it has to have, usually it's like it has a variable with x attached to it.
Mr. Hager,
Yeah?
He gave me 0 plus 0i.
Okay, that's okay. Yeah.
Which is still
It's
0.
Yeah, this is a 0. Okay? I is a root of that equation, where I is a 0. So what would be the factor? What would you plug I into and get 0 if you wrote it as a factor? So think about like if 3 was a root, you'd plug it into the factor x minus 3. So what if I is a root? Yeah?
Plug into x squared plus 1.
But we want to as a factor.
Oh, as a fact.
Yeah. Yep.
I plus 1 and I plus 1.
Factors have to have x in them because, well, they have to have whatever variable you're trying to factor. In this case, we're using an x. So what would be the factor you would plug I into, and it would come out to 0? Yeah.
X plus 1
X.
No, it's going to give 2x plus
So your variable goes here, your root goes here, and then a sign goes between them.
x plus I.
Yeah, x plus, well, in this case, x minus I. That's one of the factors.
X plus I.
And x plus I would be the other one, but we need to talk about that. All right, so it's, for now, okay, we'll pretend we don't know that other factor. But x minus I definitely has to be one of the factors of that. Because if you fill in I, we know it comes out to 0. So if you fill I in right there, I minus I is 0. Just like if 3 was a root, x minus 3 would be a factor. Okay, well, in this case, I is a root. So we're going to talk a little bit more about what I is and how would we get that other factor. Okay. So we're going to talk about both of those things. All right, so let's start with talking about what I is. So when we're dealing with imaginary numbers, I is defined to be the square root of -1. So when we had this on the other page and we took the square root of both sides, we didn't really know how to represent the square root of -1 because usually when we're dealing with the kind of numbers we've dealt with so far have been real. Well, I equaling the square root of -1, that's a definition. That is not something that you can prove. You can't answer why, really. Why is I equal to the square root of -1? It's just because it is. It's like, that's a definition. It's kind of like saying, well, why do parallel lines not cross? Because that's the definition of parallel lines. You can't prove why parallel lines don't cross. It's defined that way. Same thing here. I equals the square root of -1 because it is. We needed a symbol to represent the square root of negative numbers, and somebody chose to use the symbol that has a little vertical line with a dot above it, and that's the letter I in English. Now, because I is the square root of -1, we can figure out other things based off that. What would I squared be if I is the square root of -1? Yep.
-1.
That would be -1. And that we can prove because if you take I and raise it to the second power, that's the square root of -1 squared. And when you square and square root, those two things cancel out. And you're left with what was under the root, under the radical. How about I cubed? What do you think that would be? Yeah?
-I.
That would be -I. Because you can think of I cubed as I to the second times I to the first. And I to the second, we just figured out, is -1 times I is -I. So we have a nice formula for I cubed. We get a nice number for I squared. And how about I to the 4th? Yeah? That would be +1 because you can think of that as I to the second times I to the second. Well, I to the second is -1. So it's -1 times -1. And after that, they repeat. Because now, if you wanted to do I to the 5th, well, pull out an I to the 4th, and then multiply it by I. Well, anytime you pull out an I to the 4th, it's just 1. So now you're just left with 1 times I, which is I again. Okay, and same with I to the 6th. You could think of it as I to the 4th times I to the 2nd. So you get this repeating pattern after you do the first 4. For us, the most important 2 are going to be I to the 2nd and I. So those are the 2 we're going to deal with quite a bit. All right, and we already did that. So when we write a complex number, it's going to have I in it. And it's possible that it could have a real part that's not 0, or the real part could be 0. Okay, here's some examples of both. So with something like 2 plus 3i, that's a complex number that has a real part and an imaginary part that's not 0. 3i is a complex number. Bless you. But in that case, the real part of it is 0. So everything up here is a complex number. When we think of how imaginaries fit into the system of numbers that we know, so right now, we have real numbers. And I think it was the first day of class, I broke down all the real numbers.
Oh.
We had rational, irrational, then we went into the integers, whole numbers, counting numbers. Well, kind of like off to the side now, in another box, you have imaginaries. And together, when you take reals and imaginaries and put them, look at all those different numbers, that's the complex number system. Okay, so complex numbers are kind of broken down into 2 parts, a real part and an imaginary part. If something doesn't have a real part, like -7i and 3i, those 2 are called pure imaginary numbers. When the real part of a number is 0, that's a pure imaginary number. All right, so let's say looking at 2 plus 3i, 2 is the real part, 3 is the imaginary part. Okay, the imaginary part is just the number in front of the I. Okay? The I is just there to tell you what's in front of it is imaginary. Now, the other thing to understand about I, the way we're using I, right there. What is the I? I mean, I know it's the square root of -1. But what kind of thing is that? The square root of -1. I'll give you choices if we don't understand what I'm asking. Lucas?
Is it the imaginary part? Or just imaginary number?
It's a number. It's a number. Okay, so when you write this in math, especially in this section, you're not writing a letter. Okay, you're writing a number. Just like when you write this in math, that's not a letter. In the Greek alphabet, it's a letter. But in math, that is not used as a letter. Okay, that is used to represent a number, okay, 3.14. Well, it's the same thing with I. When you write I in math, in the English alphabet, I is a letter. But in math, that is not a letter. That stands for that number. It's a symbol for the square root of -1, just like pi is a symbol for 3.14.
Approximate, okay.
What's that? Yeah, question?
I said approximately.
Yeah, approximately, yeah. All right, so keep that in mind. Okay, so I is a symbol for a number. It just happens to also be a letter in the English alphabet. Would you ever use pi as a variable in math? Like if you were setting up a word problem, would you pick that
No,
symbol?
probably
No.
not.
You'd never use the Greek letter pi to represent an unknown because it has another meaning and that would be very confusing. Okay, same thing in this section. You'd never use I to represent an unknown because it has another meaning in this section. It's the square root of -1. So for two complex numbers to be equal to each other, that basically means that the real part of one has to match the real part of the other, and the imaginary parts also have to match. So that would mean if you had the complex number 3 plus 2i, the only other complex number that it is equal to would be what? It's the only complex number that's equal to 3 plus 2i. Yeah?
Is it 3 plus 2i?
3 plus 2i. That is the only number that is equal to 3 plus 2i itself. If you had something like 3 plus 4i, you could say, well, they partially match. The real number 3 matches the other real number of 3. But no, they're not equal, even if part of them match. For two complex numbers to be equal, both parts have to match, real and imaginary. So even though I is not a letter, when we are combining like terms, usually it happens with addition and subtraction, we can treat it like a letter, and it will work. So same thing, like if you had, let's say, x plus x, what is that? Yeah. 2x. Now I want you to answer this question the same way. What's 5 plus 5? And I want it like that. Yep. Yeah, but I'm trying to get more at like a concept here of what's happening. Yeah?
2 times 5.
2 5s. Yep. So x plus x is 2x. 5 plus 5 is 2 5s. Same idea. So if you have I plus I, even though I is a number, just like 5 is a number, you can add I plus I and say that it's 2 i's. All right, so that's the idea when you're doing complex arithmetic. You can treat I just like you would it was a variable and you're adding it, because you can do the same thing with numbers that you can with variables, with addition and subtraction. When we multiply complex numbers, we're going to end up using the double distributive property, okay, or FOIL, which means there will be times where we multiply an I times an I and get an I squared. Anytime that we get an I squared, don't leave that in the final answer. You need to change I squared to -1. To divide complex numbers, I'm going to show you a trick involving a conjugate. Because what happens with division of complex numbers is you get an I in the bottom. You can't leave I in the bottom. We're not supposed to do that. So I'm going to show you how we fix it. And let's take a look at square roots. You're going to see this come up when we do quadratic formula. What number is in front of x, even though it's not written there? Yeah.
1.
Well, in this case, it's it's -1x. So you can think of it like that. Now, when you have a product under a root, you can separate into 2 roots. Each factor under the root gets its own square root. And what is the square root of negative 1? About Ben?
Square root of negative 1 would just be I.
Yeah, it would be I. So the way we would write the final answer there is I square root of x. So kind of the big idea here is when you have a negative under a square root, it comes out in front as an I. Okay? Now the notation when we write something like this, if you have a root, you generally put the I in the front of the root. So let's say you had like I square root of 5. That is a proper way to leave the final answer. Why would you not want to do something like that? Why put the I in front and not after it? Yeah?
Because if you put it after, it may look like it's in the square root as well.
Yeah, I can't tell there. Is the I under the root or not under the root? So to avoid that confusion, we just put the I in front of the root, and there's no question that it's not under it. Now, if you had something like I square root of 9, well, it is okay to put the I after it, because once you simplify the square root of 9, you end up with 3I. And that's a more standard way to leave the final answer. Okay, so I usually goes after the number, unless it's a root. We don't want to confuse it, so we put the I in front. Okay, let's try these. So you don't really have to think about breaking it down each time by putting the negative 1 times the number. Just remember that the negative comes out as an I, and then you take the square root of the number just like you normally would. So what's the square root of negative 4 going to be? Yeah, Waylon?
Would be I and then inside the square root of positive 4.
Yep, and then when you fully simplify that, what do you got? 2I, yep, exactly. It is okay to put the I after it because the root goes away this time. How about the square root of negative 9? What's that going to be called? 3I, yep. Again, perfectly fine. Put the I after it. Okay. How about the square root of negative 7? How would we write that one? Yeah, close.
7.
That would be the square root of negative 49, 7I. So I agree, it does have to have an I though. That's good. But yeah.
I square root of 7.
Yeah, that's just going to be I square root of 7. 7's prime, so you can't simplify that root. All you can do is pull the negative out in front. And how about the square root of negative 20? Think about how you would do it as square root 20, because you need to simplify that. And then just put an I in the front of your answer. Yep.
2I square root of 5.
Perfect. 2I square root of 5. Because the square root of 20 would be 2 root 5. But this is negative 20, so it's 2I root 5. Okay, any questions on those? Okay, so again, you're going to see that come up when we get into quadratic formula, and you have to take the square root of a negative. Okay, so let's try one example of add, subtract, multiply, divide complex numbers, and then we'll start applying that to finding roots. Okay, so to add those together, think of it as combining like terms. You can combine real parts with real parts, and imaginary with imaginary. Okay, so when we combine those together, anyone think they could give me the final answer? And remember, you can think of you can think of it like it was an x, but I want you to really remember that I is a number. Yep.
It will be 11 plus 2I.
So we get 7 plus 4 is 11, and negative 3 plus 5i plus 2a. Perfect. Right? Let's try subtraction. So with subtraction, think of it as addition, but you're distributing that negative. So it's really like a -6 and a -I that you're combining with what's in front. Okay. Anyone think they can give me the answer to that?
What would be -2 minus 3?
So we get 4 minus 6. That's going to give me -2. And then we have -2i minus 1i minus 3i. So that's an I right there. Okay, any question on that one? Okay, so that's adding and subtracting. Okay, multiply. When we multiply, do it like you would do the double distributive property. Some people learn it as FOIL. Okay, either way. So let's do that out and see what we get. Lizzie, what's 2 times 5 going to give me? What is it?
10.
10, yep. So 10. And 2 times -I, 8, what's that going to be?
-2i.
So I'm just going to do that off to the side for a second, -2i. And Michael, 5 times 3i?
15, right?
So that gives me 15i. 15i, -2i is 13i. Kaylee, what about 3i times -I? Let's start with this. Positive times negative. Yeah, positive times negative is going to be a negative, so we're going to start with that. And then what about 3i times I? You already took care of the negative, so just think of it as 3i times I. 3i squared. Yep. Okay. You're okay. So 3i squared. Okay. Any questions up to that stuff? Yeah.
Why'd you get 13i?
13i, that was -2i plus 15i. So the outer and the inner combined together when we FOIL it. Yep.
Would you have simplify the I squared?
Yes, yes. If you leave I squared in there, that is not simplified. What did we say earlier I squared is? Yeah.
E squared root n.
No, I squared is not, I is the square root of
Oh,
-1.
so that's -1.
That's -1. And now we have 10 plus 13i. -3 times -1 is plus 3. So what do I get for a final answer? Yeah.
13 plus 13.
Yeah. Good. Just a coincidence, the real and imaginary part are the same. That usually doesn't happen. Okay, but remember, I squared is not simplified. So we need to make sure you change that to -1 and then combine it with, usually you have another number you can combine it with. So that would be a proper final answer. All right, so last review concept, and then we're going to get into some roots, is division. Okay, to divide two complex numbers, the only thing you have to remember is you just can't leave I in the bottom. So the way you fix having I in the bottom is to use what's called a conjugate.
It's just like the opposite, basically.
Yeah, the conjugate is, it's the imaginary part is changed to be the opposite. So we'll try some examples. So the real part stays the same, and you change the sign of the imaginary part. So if your complex number was a plus bi, the conjugate is a minus bi. So if you had 3 plus 2i, what would be the conjugate of that?
3 minus 2.
3 minus 2i. How about the conjugate of 4 minus 5i? Yep. 4 plus 5i. And what about 3i? Yeah? negative 3i. Good. And 6. 6. Yeah, same thing. You could think of 6, the original one, is like 6 plus 0i. The conjugate would be 6 minus 0i. Same thing. And the conjugate is going to be a really important concept, well, for two things. One, when we do division, we need to use it. And two, I put a question mark, where was it, right? When we were factoring something earlier. And I said, what would this other factor be? Well, it happens to be the conjugate of the first one. We haven't really gone over that yet, but if you FOIL x minus I and x plus I together, you will get that as an answer. Right? So conjugate, definitely an important idea. So any question on how to find a conjugate from a number? Okay. So how do we use that to do division? Well, we don't really do division. To do division, we do multiplication. And what we do is we multiply top and bottom by the conjugate. Specifically, the conjugate of what's in the bottom. And whenever you multiply conjugates together, you always cancel out all the i's. If you multiply conjugates together and you still have an I left in the spot that you multiplied the conjugates, you did something wrong. Okay, so to divide two complex numbers, multiply top and bottom by the conjugate of what's in the bottom. So what am I going to multiply top and bottom by in this case? Yeah.
2 plus 3i.
2 plus 3i. Now I can tell you the bottom is already, I know what it's going to come out to. It's 13. Okay. And there's a quick way that you can multiply conjugates together without really foiling them. Okay, we'll foil them this time, but then I'm going to show you the quick way to get 13 in the bottom. Okay, let's do the top first. When I multiply these out, so I'm going to start with 10. How many i's am I going to end up with
4.
in the middle when I FOIL that out on top?
13.
17. Okay, so you're going to get 15i plus 2i, so that's 17i. And then what's going to be the term on the end here? You don't have to simplify it yet. Yep. 3i squared. Okay. Now we'll come back to simplifying the top. Let's do the bottom. So we get 2 times 2 is 4. What's 2 times 3i? Yeah, Lucas.
2 times 3 is 6i.
6i. And what's 2 times negative 3i?
Negative 6i.
Negative 6i. So when you're foiling conjugates, the outer and the inner are always going to cancel each other out if they're written in a plus bi format. You get 6i, negative 6i. That number always starts as a minus, and it's going to be minus 9i squared. Okay, so let's come back to that. Now we'll clean that up a little more. 3i squared is really what number? Joe? Negative 3. So what am I going to end up with in the top when I simplify 10 plus 17i minus 3? Yeah, cool.
7 plus 17i.
7 plus 17i, perfect. And now the bottom, 9i squared is really what number? Negative 9. What's 4 minus negative 9?
9. Or 13, sorry.
13. And that's what I said at the very beginning, that the bottom was going to come out to, 13. So all that I did, you don't have to FOIL out 13, or the bottom like we did here to get 13. If you just take the first number and square it, take the number in front of I and square it, and add the two together, you can very quickly get your denominator. Because the outer and the inner are always going to cancel. If that trick doesn't make sense, squaring the two numbers I circled in blue, then just FOIL it out every time, but eventually you'll probably realize that FOILing half the steps you do is a waste of time because it cancels out. Okay. Now that answer that we have there, 7 plus 17i, that is not standard form. Okay. Standard form is you have a real part, could be a plus or a minus, and then an imaginary part with an I next to it. Not one big fraction like that. So if I was going to simplify this one, what would be my real part? What would go in this first box? Yep.
7 over 13.
Yep, 7 over 13. And what would go in the second box? Yep,
17.
17 over 13. If it says to leave your answer in standard form, that is how you would need to leave it. And in this case, it's a plus. So 7/13 plus 17/13 I. So you're just splitting each number in the numerator separate over 13. All right. So that's the review of complex numbers. Any question on that? So now let's use all those ideas to solve for roots. So now we know how to work with basic arithmetic with complex numbers. So let's see what happens. Okay, let's find the zeros of that. X squared plus x plus 1. Now, I'm not guaranteeing that there's going to be complex answers here. I just said find the zeros. Maybe this is just like a problem we did last week. Maybe there's no complex numbers. Maybe there are. We'll have to see. Okay, what? Because the highest exponent is a 2 here, what kind of equation is that? Yep.
Quadratic.
It's quadratic. So there's no need for rational root theorem or synthetic division. You can jump right to finding the roots using factoring or quadratic formula. I don't think that's going to be factorable with real numbers, so let's go to quadratic formula. Because trying to factor with imaginary numbers sometimes confuses people. That's kind of what I was doing right here. X plus I and x minus I. Let's go to quadratic formula. Okay, so in this case, Ryan, what's A?
Maybe x squared.
You're looking in the right area, but it's not a variable. Yeah?
A 0?
Well, if it was 0, then we wouldn't see an x squared there. And we wouldn't need quadratic formula if A is 0. 1, right? A is the coefficient of the x squared term, so you're looking in the right area, but it's the number in front. How about B?
1.
1. And C?
1.
Exciting. Okay, so they're all 1. So we're going to fill those into quadratic formula and see what we get. So negative B. Actually, I already wrote the formula when we were reviewing, so I'm just going to plug into it. So negative B plus or minus B squared 4AC all over 2A. So that gives me negative 1 plus or minus what's going to be under the square root? Yeah?
Negative 3.
Negative 3 over 2. And the only thing I can do is just simplify that square root of -3. And that will be my final answer. What's the square root of -3? Yeah.
I times square root.
I square root. Perfect. And that's it. So now that we know that's the roots to this problem, does that mean if I write that number comma 0, it would be the x-intercept? Because usually when you write the root comma 0, that's your x-intercept.
No,
Why not?
because it's plus or minus, right?
Right, if I wrote both of them, like that number with the plus comma 0 and then that number with the minus comma 0, would those be my x-intercepts?
No, because it's imaginary.
No, 'cause they're imaginary. You're not going to see those on the graph. There is no way to get imaginary answers on your calculator. So you have to either factor or use quadratic formula. This is a parabola that never crosses the x-axis. Any question on that? Okay. So notice if we go back to this problem, your two answers were -1 plus, and if I write it in standard form, you'd have -1/2 plus root 3 over 2i. That's the first answer. And -1/2 minus root 3 over 2i. That's what your answers look like in standard form. Didn't say to find the answers in standard form, so I would accept what we had originally. But look at these two numbers. -1/2 plus root 3 over 2i, -1/2 minus root 3 over 2i. What do you call those two things? They're similar except for the sign in the middle.
Improper fractions.
No, not improper fractions, yeah.
Conjugate.
These are conjugates. Okay, the quadratic formula gives you two answers that are conjugates. And that is something that always happens when you're finding roots of complex roots. Complex roots always occur in pairs. You cannot have an odd amount of complex roots. It has to be an even amount. You could have 2 complex roots, 4, 6, but you could not have 3. That's impossible. So when you are finding complex roots, knowing that they occur in pairs will help you because they always occur in conjugate pairs. So if you know, let's say 1 plus 2i is a root, then you automatically know 1 minus 2i is a root. So it's like you get 2 for 1. Okay? Complex roots always occur in pairs, specifically conjugate pairs. So all the theorems that we've learned, we didn't really talk a lot about factor theorem. We use remainder theorem, which is pretty similar. But all the theorems that we learned last week, rational root theorem, synthetic division, they all work with complex numbers. All right, so we're going to show that 1 minus 2i is a 0. Now, if I had a real number, and I said to you, show that 5 is a 0, one way to do it is with synthetic division. Okay, and I'm going to do it with synthetic division because it will take the cubic and bring it down to a quadratic, which then, if the next question was, find all other zeros besides that one, then I could do it. Okay. But that's why I'm going to do it with synthetic division. So the number that you're trying to prove is a root. You put on the outside. And then you put your coefficients on the inside. Can somebody tell me what would my coefficients be in this case? Yep,
1, 0, 1, and 10.
good. 1, 0, 1, 10. You got to put in a 0 for that x squared. And now, as long as it's not a trick question, they're telling me to prove that this is a root. What does that mean I'm going to get for that last number right there? Yeah, I should get 0. Yep. So let's go through and see what happens. So it doesn't start off too bad, all right? First thing you do is you bring down the 1. And now you multiply that to what's on the outside, but it's distributive. So 1 times the 1, and 1 times the negative 2i. Well, in this case, you're just distributing 1. So we get 1 minus 2i. Now we're going to add that column up. What do you get when you add what's in that column?
Minus 2i.
That's part of it.
Or 1 minus 2i.
1 minus 2i. Okay, now here's where it gets a little bit more annoying than regular synthetic division. What do I have to do with this 1 minus 2i?
Multiply then by 1 minus 2i.
Right, I have to multiply what I got in that column by what was on the outside. Okay, so that's going to involve foiling. So I'm going to do that off to the side, and then I'm going to put the answer right there. So we've got 1 minus 2i from the bottom of the second column times the number on the outside. Okay, FOIL that out. We get 1. What am I going to get for my I term in the middle? Yep,
Negative 4i.
negative 4i. And what's negative 2i times negative 2i? As simplified as you can give it to me. Negative 2i times negative 2i. Yep,
Negative 4.
correct. That is negative 4. Okay, combine like terms. 1 minus 4 gives me negative 3. Minus 4i. Add that to what you have above and put the answer in the bottom of the third column. So what do we get when we add that column up? Yeah,
Negative 2 minus 4i.
negative 2 minus 4i. All right. And now what do I have to do to get the answer that's going to go right there?
Gotta do it again.
Do it again? All right, tell me what to do.
So you gotta multiply negative 2 minus 4i by 1 minus negative 2i.
1 minus 2i. Okay, so let's multiply that out. We get negative 2. And then we're going to get, what am I going to get in the middle for my i's?
4i and negative 4i, so those cancel.
4i, yep, and negative 4i. So I don't have any i's in the middle. What's negative 4i times negative 2i?
Negative 8i squared. Or no, 8i squared.
That's going to be 8i squared, which is what number?
That's 8.
8i squared. That I squared is going to change that number.
Oh, negative.
Negative 8. And what's negative 2 minus 8?
Negative 10.
Negative 10. Add that last column.
Oh, that's crazy.
0. So we just proved that 1 minus 2i is a root of the original problem. X cubed plus x plus 10. We're not going to worry too much about the quotient right now because the quotient has coefficients that would be imaginary. So when we do a problem where we take this a step further and then we look at the quotient, I'm going to make sure that the quotient doesn't come out with imaginaries like that. Okay, I'll make it so they end up canceling. All right. Any question on how we showed that that was a root? So we know 1 minus 2i is a root. What else is a root? Yeah.
1 plus 2i.
1 plus 2i. Yep. has to also be a root. And if we did this process with 1 plus 2i, that on the quotient, we could simplify this even further, and then we could get what would be left for our final answer. Right? We could find all 3 answers to this problem. And there are 3, because it's a cubic. We've got 2 of them, 1 plus 2i, 1 minus 2i. What kind of answer would the last one have to be?
Real.
It would have to be real, because it's a cubic, and every cubic crosses the x-axis. Has to. So once you get your 2 imaginaries, and if you did the synthetic division one more time, you would be left with a linear polynomial, which you could then find the real root of. And it would just be degree 1, so it would be a very easy equation to solve. Like 2x plus 4 equals 7. Be something like that. Okay. Cover that one. That's all I want to do. Well, I kind of just touched on this. Why do odd degree polynomials always have to have at least one real 0? I talked about it for the cubic in the last problem, but it's actually true for any odd degree polynomial. Yeah?
That's true because they always cross the x-axis at least one point because each end has a different, going either positive or negative, on opposite on each end.
Okay, so the end behavior is one end is up, one end is down, and there's something else very important about polynomials. Polynomials are just because one end goes up and one goes down, that does not guarantee it's going to cross the x-axis.
Oh.
But this is a polynomial, and polynomials are,
Infinitely long.
yes, they are infinitely long. What else about them now? Yeah?
Continuous.
They are continuous. That's the key. One end goes down, one end goes up. You never lift your pencil the whole time, so you have to cross the x-axis. Yep. Okay. So let's now try to find the zeros of x cubed minus 1. Okay. What's the degree on that equation? Yeah. 3. That's not a quadratic, so you're not plugging that into the quadratic formula. Somehow you've got to turn this into a quadratic. How are we going to try to start to figure out what could be a root in this problem? Because they didn't give us one. What do we use as kind of our starting point to find roots? Yeah?
If we do a quadratic formula.
No, this
Nope.
is cubic.
Can't do quadratic formula on a cubic. It's a process we learned. I think I reviewed it a little bit. Yeah.
Rational root theorem?
Right. The only thing that's going to help us is if we can find a root that's rational and then divide through it by synthetic division, and that'll turn it into a quadratic. Then you can use quadratic formula. But until that exponent is a 2, you're not doing quadratic formula. Okay. What are the factors of the constant in this problem? 1 and?
Negative 1.
And the factors of q? The leading coefficient?
Negative 1. Negative 1.
And 1. So not really much interesting with p and q this time. So what are all the possible rational roots?
Plus or minus 1 over plus or minus 1.
Plus or minus, yeah, so it's really just plus or minus 1. And now, normally I would use the graphing calculator to narrow that list down, but it's so small, and the formula is so simple, I don't even need to. I can plug these numbers in quicker and figure out which one comes out to 0. Which number can you plug in from this list, and it will come out to 0? Yeah?
1.
1. Yeah. Again, if I didn't know that, I would use the graphing calculator. So I know 1 is a root. What am I going to do with that root to turn that cubic into a quadratic? Yeah,
Synthetic division.
right. I'm going to pull out the factor that corresponds to the root. So I'm going to factor out an x minus 1. So to do that, I can do long division, or I can do synthetic. 1, 0 squared, 0 linear, and there's my constant. Okay, so bring down the 1. 1 times 1, 1, 1 times 1, 1, 1 times 1, remainder 0. Okay, so what's my quotient in this case? Yeah.
X squared plus X plus 1.
X squared plus X plus 1. Set that equal to 0, and now find the roots of it. But look at that. X squared plus X plus 1. Find the zeros of X squared plus X plus 1. We already did that problem somewhere. Right there. That was example 4. So we already know the other two roots. Negative 1/2 plus root 3 over 2i, and negative 1/2 minus root 3 over 2i. So back here. Okay, so we got 1 as a root. Negative 1/2 plus root 3 over 2i, and minus. If you want to see how to get those other two roots again, just look back at example, I think it was example 4. Yeah, it was example 4. So there's your 3 answers. You will always have as many answers as the degree. You have to. Because now we're taking into account the complex answers. Any question on that one? Here. Okay, we did that. So more just kind of a wording thing that you might see in the book. In example 6, it was f of x equals x cubed minus 1. And we basically solved that equation. We found all the roots. So another way to think of that equation, you could add 1 to both sides. And if you thought of it that way, instead of the way we did it, what would you need to do on both sides now to get x alone? Yeah.
Cube root.
Right, you take the cube root of both sides. So what we really did in this problem is we found all of the cube roots of the number 1. These are the 3 answers. That's the cube root of 1, that's the other cube root of 1, and that's the third cube, that's the other cube root. Okay. Cube root always has 3 answers. And that's, again, just thinking of that problem a little bit differently. Still setting it equal to 0, but adding 1 to both sides, and now taking the cube root. But the thing is, how would you take the cube root and get the imaginary answers? Well, the only way to do that is the process I showed you the first time. You could get the real answer by taking, on your calculator, but you can't get the imaginary answers thinking of the problem this way. It doesn't work. And this could be more complicated. What if it was x cubed plus 3x squared plus 5x minus 1? Well, now it's not as simple as just adding 1 to both sides and taking the cube root to get x alone. So you'd have to do it the first way. So when we found the cube roots, we found the cube roots of a very particular number. Okay, it was 1. In our book, sometimes the way they write the number 1 is they use the word unity. So like if you see a problem that says, find the 4th roots of unity, it basically just means set up an equation like this and find the 4th roots of 1. So you'd be doing something like this. That's the equation you would solve to find the 4th roots of 1. That's the equation you would solve to find the cube roots of 1. So anytime you want to find roots of unity, you basically do this. All you do is change the number that would be your exponent to whatever type of root they're asking you to do. Cube root, fourth root, things like that. And then, if you think of bringing that 1 to the other side, you'd have something like x to a power minus 1 equals 0. And the goal now is to solve that. Whether you use rational root theorem, quadratic formula, synthetic division, that depends on the problem. But this is the type of equation we're going to be setting up in the next problem. Okay, so let's try that on this one. So the first step here would be to understand what the equation is they want you to solve. They want you to set up an equation where you would be taking the fourth root of each side to solve it. If you're going to be taking a fourth root, what is the exponent you would need on x that would force you to take a fourth root to cancel out the exponent? Yeah, right. It would have to be to the fourth power. And they want you to find the fourth roots of unity, which means what number? 1. And now think about setting that equal to 0 and solving it. And that's what I want you to do. So finding the fourth roots of unity means to set up that equation, which really means find the roots of that equation. Now that you don't need, you could do rational root theorem and synthetic division, but if you realize this factors, it's going to go a lot quicker. How does x to the fourth minus 1 factor? It has to factor, it's only 2 terms, and it's a difference of perfect squares. Yeah?
X squared plus 1, x squared minus 1.
Perfect. So that's how we factor it the first time. Then we can factor it one more time because x squared minus 1 is a difference of 2 factors. How does x squared minus 1 factor? Yeah?
X plus 1, x minus 1.
Perfect. And now set all of those equal to 0, and there's your answers. So we get x squared plus 1 equals 0, x plus 1 equals 0, x minus 1 equals 0. Okay. Here we're going to get negative 1. Here we get positive 1.
For that one, you get 1 ugly.
So what's going to happen here?
Plus or minus 1, actually.
X squared is going to equal
The square root 1 or I. Right?
Negative 1.
x squared is going to be negative 1.
And then it's x equals the square root of negative 1 or I.
Something we're missing there. X is the square root of negative 1, but we're missing something.
Plus or minus.
Plus or minus. And what is the square root of negative 1? So we get x equals I, and x equals negative I. So those are the 4 answers to this problem. I, negative I, 1, negative 1.
Okay. Cool with it. I figured out.
And you don't have to do any synthetic, you could do synthetic division, that's going to take longer. Factoring is much, much faster. Any question on that one? Okay. Let me see. Okay. So we just did that, and then I think that's the last page. Yeah. So in all those examples we just did, what I want you to notice is that the number of answers that we got was always equal to the degree of the polynomial. If you're solving a 4th degree problem, you will have 4 answers. 3rd degree problem will have 3 answers. And there's a theorem that talks about that, and that is the linear factorization theorem. And what that theorem says is that if you have a polynomial and the degree is greater than 0, and it has real coefficients, then when you factor it, it will factor into as many factors as the degree. So for example, if you were to try to factor that, how many sets of parentheses would you write when you factor that? Based on that theorem. Yep, 3. And at this point, you guys should be able to do that. Maybe not, I couldn't do it that quick. But I would use the rational root theorem. I would hopefully find one that works, and that would turn the cubic into a quadratic, which then I could solve by factoring. And that is how this one factors. How about this one? What type of polynomial, what would have been the degree of the polynomial that that problem came from? Because it factored into, yeah? Yeah, that would have come from a degree 5 polynomial. And a degree 5 polynomial does have 5 answers. In this case, some of the answers are repeated. -1, -1, 2, 2, and 2. So when you are factoring something, the factors do not need to be distinct. You can have repeats. That's okay. So the fancy word for how many times a root occurs, that's called multiplicity. So -2 is a root, and that one occurred twice. So we say it has a multiplicity of 2. I didn't write the last one. 2 is a root, and how many times does the number 2 occur as a root? Yeah,
3 times.
3 times. Okay, we're not gonna. Okay, so if I give you a polynomial and it's higher than a quadratic, then the rational root theorem has to work to be able to get it down to a quadratic. I would never give you a cubic or higher that you can't use rational root theorem and then synthetic division on. If that did happen, then we'd have to come up with another way to try to solve it. So that is the homework for tonight. The only thing we didn't specifically talk about is, like if I told you that 3 and 2 are roots, we know that x minus 3 and x minus 2 are the factors. You can do exactly the same thing with imaginaries. If I told you that 5 plus 2i and 5 minus 2i were factors, you can write them as x minus that root and x minus the other root, just like we did right here. So we might have to talk a little bit about how to do that, just foiling tomorrow. But we can look at that tomorrow. So homework is on page 193.